All right, here we go. Second lesson of the circles unit. I hope you had as much fun watching that first lesson as I had making it. All right, this one seems like it's going to be not quite so much information as that first one. What you might notice about this, first of all, is that we're skipping ahead of it to 10.5 and 10.8. Long story short, it has to do with the calendar. We got certain things, we got certain interruptions this time of year with interim and Lunar New Year and all kinds of stuff. So we're trying to put the stuff that goes together that makes most sense where the breaks fall in certain times. Anyway, we are going to pick up some more Chapter 10 stuff that happened before this next time. Anyway, today this is what we're tasked with: tangents and equations of circles. The other thing I might want to mention, as long as I'm talking macro level book stuff, there's some stuff in the book for equations of circles that goes way beyond what we really need to teach you this year. So if you start looking through the book and start going for every single problem you can find about equations of a circle, you're going to get some stuff that goes way harder than what we need to do on the test. So when you look at what's assigned at the end of this, we pick those very carefully to only make sure we got stuff that's going to be like what's on the test. All right, so first of all, let's talk about tangents. Tangent, this is a very common thing you need to know about, unfortunately has very little to do with the way we use tangent on the test you took last week. Tangent in trigonometry language and tangent in circle language kind of mean different things. They are actually related, but we don't get to the point of being able to explain to you really how closely they are related this year. So for now, you kind of have to think of it as two different things. All right, so it's the name of this line when a line intersects a circle exactly in one point. A line could easily intersect a circle in 2 points, or not at all, but in between there, if it just comes by and kind of nicks the circle like the ball bouncing off the wall here, if it just hits at 1 point, that is called a tangent line. And that's called the point of tangency. You could have a line that goes tangent to 2 circles. That's called a common tangent. There could be one like this. You could also have a common tangent. Oh, could I do this easily? You also have a common tangent that looks more kind of like this. I don't think I got that perfectly, but you could imagine such a thing. Yeah, I'm going to take that off because I didn't do that right. But yeah, there's a way to do common tangents that way too. They're actually called different things, but I don't know that we need to bother you with that. A line tangent to 2 circles is called a common tangent. Okay, some theorems about tangents. If you have a line tangent to a circle, the radius at the point of tangency will always be perpendicular to that line of tangency. In fact, if you're in Sketchpad, you want to construct a tangent, that's how you do it. You make a radius first, and then you make the perpendicular at the end of that radius, and what you'll have is the tangent. And it's an if and only if. It's a biconditional. And it's originally a biconditional in the book, which is really nice. So tangents and radii are always perpendicular. They intersect right there on the circle. Quasi-related to that, this is pretty easy to prove once you believe this one, that if you pick some random point outside the circle and draw both tangents, reminds me of the picture of how ellipses work. You think of this as the ellipse diagram. Also kind of looks like an ice cream cone diagram, kind of. Anyway, when this happens, you pick a point outside and you draw the tangent to each extreme direction of the circle, sort of. Those tangents have to be congruent. So the distance from B to this point of tangency A and from B to this point of tangency C, those are congruent triangles. If we drew triangle BAC, it would be isosceles if I connected these with this chord here. All right, things you might want to know. So, polygon is circumscribed about a circle if every side of the polygon hits the circle just in one point. If it's tangent, kind of goes around the outside. We could make some conclusions about the segments in this picture pretty easily once we apply this theorem. Like these kind of things are congruent. Like I would know the distance from here to here is congruent to this part down here, just to the point of tangency. We'll see that in the problem, so file that away. And the other half of this, see how fast we're moving? If the tangent stuff didn't make sense, you can go back and rewind, but that's really all there was to talk about with tangent and terminology. We'll do some problems about it in a second, but that's all there is about tangent. The other half of this today is about equations of a circle. So we're talking about putting a circle on the coordinate plane and talking about the two-dimensional x and y coordinate graph, where the graph of the equation is the points on a circle. You've graphed lines before in algebra, you've graphed parabolas, so curvy things shouldn't be new to you. Now we're going to talk about how you would describe all the points that are on the circle with an xy equation. If you were to do x squared plus y squared equals r squared as some sort of equation, you're supposed to enter that on your calculator, or ask ask a graph to show you all the points where this is true. You pick some number for r, because this hopefully should look familiar to you as the Pythagorean theorem. This would be the place where all the distances from 0, 0 to this coordinate out here, x comma y, would all be the same distance r. Think about this triangle right here, and some random point that's supposed to be on my circle, x comma y, and how that point gets to be able to say that it's on the circle. You got to think about, well, what's the definition of circle? What is it that makes that thing a circle? What is it that I need every point on the circle? What property do I need that circle to have? And it has to be this certain distance we call r. It has to be that distance away from the center. And here we're gonna start talking about circles where the center is the origin, because that's the easiest place to start. So if the center is 0, 0, the distance out here is supposed to be r. Well, I could find that distance using the x and y coordinates. Remember when we found distance on the coordinate plane long ago? It was Pythagorean theorem. X, if this is the point x comma y, x can be represented by this little length here. X is the x coordinate is the amount that we need to kind of go east of center to figure out where this point is, and y is the amount we have to kind of go north of center. So that's the beauty of coordinates. We get these perpendicular distances. Here's a representation of the x coordinate, here's a representation of the y coordinate, and I know, since it's on the circle, that the distance all the way out here to 0, 0 to x, y, that has to be r. So I know x squared plus y squared equals r squared. So if I graphed all such points, x comma y, where they were talking about the same r squared, this would describe all of the points on the circle. So some random point up in here, yeah, x is negative, y is positive, but if I square x and square y, let me draw it. Say I have a different x comma y, and it's kind of up here. So x is some weird random negative number like this, y is some number like that. But I know it is this far away from the center. This is a different x. Oh, I'll call it, let's just change colors here. This is easy to see. I have green x and green y. Well, green x squared plus green y squared still has to be green r squared. Or sorry, well, I guess it's red r squared. It still has to be the same r squared as this one. But that's going to be true no matter where I draw this on the circle. It gets tricky when we talk about circles that don't have a certain radius or aren't necessarily centered at the origin. So we use the distance formula to find, or basically Pythagorean theorem, to find the lengths of the sides of the right triangle, and in turn the hypotenuse, which is always the radius of any one of those points. What ends up happening is, if you know the center of the circle and you know the radius of the circle, this is how we adjust the equation, that original equation where it's at 0, 0, for this. This will shift the center of the circle to the point. Let me just write it on here. Well, I guess it says right here. The center is h comma k. If you know what the center is, you plug h in here and you plug k in here. And the radius is, again, just our friend r. Let me do an actual one with a real. When I get to the problems, we'll see how that works a lot better. Okay, back to tangents. Segment OT is tangent. Okay, so this is a tangent. Q is some point on the circle. If OR is 6 and OT is 10, find RT. Well, the theorem we learned about was that tangents and radius at the same point, that has to be perpendicular. So if I know that's 10 and that's 6, this is simply a right triangle. All I got to do is 6 squared plus 10 squared equals what I need squared. So this is the square root of Pythagorean theorem in my head really fast. This is the square root of 136. Okay. If OT is 4, okay, I'm going to redo this now. If OT is 4, well, that's still perpendicular. If OT is 4 now, and QT is 2, and RQ is x, find x. Well, that seems like a mean thing to do. It's not a very good looking x. Well, the trick on a lot of these problems, don't forget about, is this is a circle in the first place. So the distance from R to Q ought to be the same distance as the distance from R to O. Those are two different radiuses of the same circle. So now I have a description of everything in this triangle, and I know it's a right triangle again. So I know that x squared plus 4 squared equals the hypotenuse squared. Don't let that scare you. It's just that big. I have some nasty algebra to think about now, but it's not too bad. X squared plus 16 equals x squared plus, oh gosh, 4x plus 4. Oh, things are going to cancel. This isn't going to be so bad. 4x equals 12. So x is going to be 3. And you could check that. You could put a 3 here and a 4 here, and oh, look, 3, 4, 5. Perfect. It's a nice right triangle. Okay, find x if This triangle has a perimeter of 56 and is circumscribed about this triangle. Okay, so yeah, remember we learned this about tangent segments. The segment from C to G is tangent, and the segment from C to E is tangent. So from point C outside the triangle, the two segments that are tangent are supposed to be congruent. Likewise, D to E should equal D to F. Oops, that's 14. And B to F should equal B to G. So I have representation now for the whole perimeter. This whole perimeter, which is supposed to be 56, is equal to all this stuff added up. 14 plus 4 plus 4 plus x plus 14 if you go all the way around the triangle. This is, let me pause so I don't have to go to part 2. I get x equals 10 on that. Check my algebra. Been known to make mistakes before. All right, find the center and radius of each circle. Okay, for these, all you have to do is identify from the formula, back from a little ways earlier in your notes. Just figure out where the center is supposed to plug in here and what the radius is supposed to plug in and look like. So the center of this thing, go back and look at that formula again, is going to be at 3, -5. So basically we change the signs on whatever's here. We call that the center. X goes with X, Y goes with Y. And we know that r squared equals 9. That's how this works. So we can say for sure that r is 3. It doesn't make sense for r to be negative. Same thing here. The center is going to be at 2, 0. That's how a 0 looks as a center. And I know that r squared is 54. So we can just say r is the positive square root of 54. Great. Write the equation of this stuff. Well, this is always the same, x minus something squared, plus, every time you do a circle equation, you don't even have to look at their circle yet. You know they're going to look like this. That's a plus. Equals radius squared. It's a great big fancy version of the Pythagorean theorem, really, a squared plus b squared equals c squared. The thing that goes in here is the -8. Watch how I do that, -8. This part is -3. Watch how I do that, -3. And the part out here is the radius squared. I can just do this. Now I can clean that up a little bit. Actually, this would be fine. If you really wanted to, 2 times the square root of 3 squared is 4 times 3. That's 12. So you could write the 12. Of course, I would have to take the square off. If you take 2 times square root of 3 times 2 times square root of 3, end up with 12. So you could either end that with this way or this way. But this kind of is as simple as it gets on that side. Don't try to get fancy and simplify that up anymore. Calculator wouldn't like it any simpler than that either. All right, same thing here. I just need to find this equation. Well, to find the equation, I need the center, and I need the radius. The center looks like it's probably at, what is that, 4, 4. So again, these circle equations always go like this. X minus something squared plus y minus something squared equals something squared. The center goes in here at 4, 4. That's easy. Then I just need the radius. Well, I can count the radius here. If that point's on the circle and that's the center, whoa, nice straight line. This is supposed to be 4. Oh, the radius is also 4. You could leave this way, or you could say that equals 16. Either way. All right, one screen left. Find the equation of this circle, given that AB is the diameter. Now, they didn't put the axes on here, but it's pretty easy to tell since it's horizontal. This diameter is 12, so that tells me that the radius is 6. That's kind of nice. But I also need to know the coordinates of the center, which appears to be right here. If this is -5, 5, and this is 7, 5. By the way, I found that 12 just by subtracting the 5 and the -5 and the 7. I kind of have to know the midpoint here, right? Because if these are 2 points along a diameter, the midpoint's going to be halfway between. Or you could just about count -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7. That works too. Or I could use the midpoint formula. I could find it that way. But once I have the center and the radius, I can plug them in. Equations of circles look like this. Haven't thought about my circle yet. And I plug in these 3 spaces, these 3 things. Center at 1, 5, radius of 6. I have a little time. Maybe I could explain that midpoint thing a little better. The midpoint is, we had a formula for midpoint long ago. It was something like this. You plug in the x values together and the y values together, and you find their averages by adding together, divide by 2, and you'll notice you'll get this. Okay, great, just in time. I will see you in class. How about that?